Okay, I'm still waiting for the slides.
Well, I'll get us started while we wait for the slides. They're not as essential. I can also use the conversation as well. So hello, everyone. Welcome to our interactive session where we'll try some new ways of trying to engage each other in the conversation. We call this the brain writing session. And what brain writing means is I learned this from Heiko Kozia like a number of years ago, which is giving each other some time to think and address some questions and then react rather than reacting to the communicative, more verbal output. And so we prepared a number of questions based on the papers and the conversations that we've been having. And we're hoping that it's going to be fun. And through that interaction, we'll facilitate some conversation throughout the next half hour. So if I kind of summarize what brain writing is an idea generation technique, and participants write down their ideas in response to particular prompts and questions without for a few minutes without talking. Since we're in this virtual environment, it's also a little fitting to the context we're here. And please give me some patience here. I have never used Slido. I'm hoping it's going to work. I've tried it a number of times, but hopefully the technology will help me there. So the goal of the conversation and the questions are to facilitate some of the hard questions that we've been asking throughout the sessions. For example, we've been talking about software engineering for AI versus AI engineering. I think there were a couple of papers that touched upon some of the challenges and where the disciplines sit. So there are a couple of questions related to that. And also the top industrial challenges in building and using these systems and where research should focus on. So the questions will focus on these aspects, and then we'll step back and use maybe the chat function of Midspace to address a last question, which is what are the mistakes and pitfalls the software engineering research community should avoid and or should engage more in to be able to address these questions. With that, so we're going to use Slido. So please, in your browsers, okay, so you have the slides. So you could go to slide 3, Tom. That has the instructions. Yes. So in your browser, another tab, visit Slido, and our session number is 03122181. And I think I can share that tab, Tom. So let me share the Slido and let's see if we'll be able to interact through these. So, all right. Can I share now, Tom? I think I will be able to share the Chrome tab that I have. Right. Do you see my Chrome screen?
Yes.
Yes.
Yes?
Yeah.
Perfect. All right, so I'll give everyone a minute to set up. So, and since I'm on the screen share mode, so I'm going to rely on you, Tom, if I'm running too fast or too quick and if there are chat questions. All right, okay. Is everybody ready? I'm very much hoping this is going to be fun. So let's see. What are the top challenges in building AI-enabled systems? And if this works the way it's supposed to work, as you type your answers, we're going to start saying, all right. 3 participants, 2 participants. The session has 30 people, so all right, we're... I see new participants joining, so I'll give this first one a little longer so that everybody has an opportunity to get their head around the platform and interacting with it. But needless to say, I'm over the moon now that this is working. 30 more seconds. Okay, so I think we have a number of really interesting information collected. I will summarize these later, but we have a number around data, a number around requirements, collaboration, and but some interesting ones that we're seeing overwhelming number of tools and testing and monitoring and evolving some of these systems. So I think these are all in line with the conversations that we've been having. I think the overwhelming number of tools is one that we haven't addressed so far in the papers or the discussions we had, but the others definitely were voiced. And we'll come back to these as we go through the questions. And so let's go to the next question. This is related to one of the papers, a couple of the papers that we heard throughout a day and a half so far. What skill sets the role of an AI engineer, ML engineer industry needs to include? So I don't see any participants yet on my screen. Okay, there we go. Okay. Looks like we're kind of converging in this one as well. So I know we are not maybe a huge data sample and representative of the software engineering and computer science and all the disciplines, but I would like us all to step back and think a moment. Data management and data science comes up as the top skill. Software engineering skills are definitely important, but that's not the driving skill. And this is, I think, important to reflect as we continue in the research area, as well as think about how software engineering, AI engineering, and these disciplines interact. This is good and interesting. Right. In the interest of time, I will continue. So our next question is, what should research focus on? This is, if you're seeing it in screen, it's a prioritization task. I would like you to all rank these, and we'll see how the ranks will go. So we have data, algorithms, human-computer teaming, test and validation, sustainability, eliminating mismatch between different disciplines, and the topic that I should have included but did not. I don't think there's a clear top, although data and test and validation obviously drives the list. Let's continue. So the next set of questions are more in the style of a quiz. While there's not one right answer, I had to pick a right answer. So let's see how this is going to go. I think you'll have to all join the quiz. And let's see. This is an everyone is a winner kind of a quiz. So. Okay. Let's get started. So are AI, the first question, are AI engineering and software engineering for AI two distinct fields with their corresponding practices? So we won't know how everybody will have answered. I will respond. I will share the stats at the end. They're all questions, food for thought. Okay. All right, we are overwhelmingly yes. We think there are two distinct disciplines. Then I think our responsibility as applied researchers, I'd like to call our software engineers, to really identify what are the common practices as well as different practices. And yeah, I do go back and forth between myself, not sure yet, and yes. And I think we all sit on these camps in different ways. Okay. Next one. So I picked 2 answers. So these are the answers I picked. AI is driven by. Going once, going twice. Data. So interesting, nobody said code. People, I think, is a fair answer. And in this one, the answer was data, because this was in the keynote of Christopher Wray yesterday, and also in some of his papers. So because it's a quiz, I kind of used it as my own validation in terms of bringing that. Definitely people, but again, as software engineers, food for thought, data is really what's the important artifact here that I think is driving some of the AI conversations that we may not be really focusing on as effectively yet. Next one. These are some, the next set of questions, the 3 questions are in a way to kind of challenge our minds in terms of, okay, AI versus software engineering and what are the boundaries between them. So this is targeted to that. We can verify correctness of systems without AI using today's tools and techniques, but it is not possible to verify AI-enabled systems. Some mind-twisted questions. Okay. I think I will move on so that we have some time to discussion. It depends. I think I agree with the it depends one. One of the mistakes I think we as a community fallacies we fall into is to think that we can verify existing systems and we can talk about some of the uncertainty aspects of systems even without AI. And when that is not possible, the challenges are exasperated. But I think the black and white comparison is not always helpful in us in making progress. Next one. We can manage hidden dependencies in systems without AI using today's tools like techniques, but it's not possible to manage these hidden dependencies in AI-enabled systems. Okay. And you probably have picked up my pattern by this time. So this is an important one. And so far in this conference, we haven't seen the infamous paper by the Google researchers, the hidden technical data of machine learning systems. This was a point made by them in terms of the importance of understanding hidden dependencies that are driven by data in AI systems. However, again, this is not necessarily a solved problem in systems that do not include ML, AI, or data components. So it's important when we're thinking through techniques, we think through the challenges of existing systems as well. especially if software engineering and those analysis tools are to be brought to the use of AI-enabled systems. And last but not least, it is possible to specify systems without AI using tools and techniques, but it is not possible to specify AI-enabled systems. I think this was also mentioned through a number of papers in terms of the importance of different requirements, engineering techniques when we're targeting AI-enabled systems. So. And some do believe it's possible to specify systems that do not include AI, others don't. And there's it depends because their situations might be different. Those are all the questions I have. I hope you enjoyed interacting with them, but what I'm going to do now is I'm going to stop sharing, and I promise I'm going to extract all the data that we've collected and share with all the attendees, at least for this session, so that you have them if you would like to use them. But I would like to now get back to this and address our last question, maybe to whoever who would like to address it. First of all, your reflections in terms of the questions. Now I'm kind of looking into the discussions here. Data science is a stop word, data scientific AI. We all agree that algorithms are already well established. Wow, no one has code. Tom, I agree with that. I was very surprised as well. So maybe software engineering for AI is something we want to believe, but really it's really on the data. Yes, these questions are very hard to discuss without and answer without discussion. So I now open the floor, and the last question I had was, what are the mistakes and pitfalls that as the software engineering community we should try to avoid given the context of these conversations and the questions? And in the last 7 minutes, I open the floor, and I'm following the chat. Is code is data code is generated. Yep, so that's. Any reflection, any feedback? Any questions we should have asked but did not? Hi, Jane.
Hi. Okay, so I was one of the people that said no to the last question, meaning that it should be possible to basically specify AI-enabled systems. I'll just make one quick comment from the RE perspective. I mean, in requirements engineering, as everyone knows, we have functional requirements that we specify and then non-functional ones. And it may, I mean, the way I think about it, because we're using AI on our drone systems right now, we need to be able to, kind of specify and validate them. So I think we do it with some kind of degree of satisfaction and a degree of what we expect, and maybe more in the way that we would specify non-functional requirements than functional ones. So that's why I said no, because I optimistically am trying to do that.
I do agree. And I think my it depends was the assumption that to the extent you cannot specify AI-enabled systems, I think those challenges and uncertainties exist in other systems as well. So the techniques do not necessarily mean, I can specify one, not specify the other. And we should try to specify all the systems to some level of certainty. I think that's really the point in that. And I do agree with the perception and the perspective that you bring. And I'm hoping that our attendees do agree with that as well. Because if we say we cannot, then we're in this endless generate and test mode, which is not engineering or principled design or any of the other, I think, techniques. So that's.
Yeah, while we're waiting for someone else to join, I'll just
Yeah, go ahead. And there's a
if there's
question. and
someone
I'm
else.
going to
Oh,
ask
there's a
that
question.
as
Just
well.
go ahead, go for it. Then I can make my
Yeah.
comment later.
So there's a question that Andre posed to all of us. One mixed team of researchers and engineers or separate teams? And I'm assuming by researchers, you mean the data scientists. Andre, do you want to come on and clarify the question? And maybe there are some takers within the team, the attendees.
Yeah, I can talk.
Yeah, go ahead.
I mean, you often see this in industry. You can have data scientists, you can have applied scientists, whatever the title is, right? So there are two very distinct patterns. Sometimes they work within one team on one code base, common code reviews, common everything, or they're completely separate and they just have some kind of way of interfacing, and like they run separate sprints with separate goals, and they completely separated teams within one organization. Which one people prefer and why would be interesting to know.
That is a excellent question, and I know there are some industry participants within the attendees. Any takers? I can provide some input from the perspective of the organizations that we worked with, as well as the. Luis, come on in, please. We talk enough as organizers. Go ahead.
Yeah, so I can from industry experience, but I can also see what I observed from working with some teams of AI projects, and my intuition is that we should have a team that works together and not separate teams. Mostly because we have seen that with the DevOps movement as well. We used to have the software engineers working on developing the code and the operations engineers working on making sure that it could go in production, and we know that it's not effective. So if we find a way of having everyone from different fields working together in the same project, I think we can go way far than by separating teams. But we have also seen that, in some companies, they tend to have a team creating the model and proving that the concept works, and then they hand it over to a team of experienced engineers that will actually re-implement the whole thing. But we tend to think that it's not the best environment to work on such an AI project.
So I think the software engineering field have seen similars of this phenomenon when other quality attributes entered. And of course, AI is not just a quality attribute, but like, for example, usability, security. We've seen that it works best when these skill sets are integrated within the teams. I think the data science is similar to that. I do agree.
Yeah, and on top of that, one of the keywords that I added to the cloud map was the ability of engineers to work with people with different backgrounds. I think that's also very important, because there's also this idea that we as engineers, we know how to code, we know how to build software, so we tend to be a bit arrogant. For example, no one should use Jupyter notebooks because that's not the way of building a proper project. But we should also have an attitude of trying to understand why they are using these techniques that are not perceived as efficient for a software project. And we should try to somehow work with them and see what are their challenges, and not just come up with the best engineering practice that no one really wants to use. So those are my 2 cents.
I think there's room for software engineers to contribute to make data scientists' jobs easier as well. That's a category of, I think, tools and techniques that we definitely can contribute. Data labeling and some of the tools, as you said, like if they prefer Jupyter notebooks, maybe that is the mode of interaction for them.
Yeah, maybe there's a reason for that. Yeah.
So interesting discussions on the chat as well. But I think that concludes our half hour of fame. I hope you enjoyed. I hope there were some thoughts that were triggered. And I'm really hoping we'll continue the discussion throughout the rest of the day, but also throughout our work after the conference and towards that next year as well. Right, the floor is for the papers. Thank you, everybody.
Thank you. Okay, so welcome everyone to the session on AI smells. We have 3 exciting papers for you, and when we're actually putting together the program, like these 3 papers fit perfectly, so that's why they got their own session, because they're all about different types of smells in AI systems. We have papers about code smells in AI systems, but also about data smells. And so the first presentation is going to be by Hai Ying, and please go ahead and share your screen.
Yes, thank you, Tom.
And she's going to talk about code smells for machine learning applications.
Yep. Can you see my screen?
Yes, we can.
Yeah. Okay, thank you. Hi, everyone. Welcome to today's presentation. I am Haiying Zhang. I'm from Delft University of Technology in the Netherlands. I'm supervised by Professor Louis Koos and Professor Eric van Durissen, who are also the co-author of today's paper. This work was done in the AI for Cleantech Lab, which is a collaboration between TU Delft and ING, the global Dutch bank. Today, I will be presenting our paper, CodeSmell for Machine Learning Applications. So in this presentation, I will first give you some introduction about the paper and then work through the methodology, the result we get, the discussion and the implication we received, and finally come to the conclusion. So you probably already know that machine learning is very popular nowadays. Big companies have adopted machine learning as the core components, for example, making the recommendation system or building a translator. Since we all want to build reliable software, there are a growing concern about the software quality. However, there is limited guidelines. And the software, the data scientists are lack of engineering experience, but they are eager to learn. And as for the code quality aspect, there are some general advice on the code. For example, you shouldn't write duplicated code, but there are no coding advice specific to the machine learning applications. So these problems motivates us to come up with research questions. What are the recurrent code issues that might arise from the peculiarity of the machine learning applications? We try to mine code smells specific to machine learning application and answer this question. So to identify code smell, we first need to define what code smell is. We took the code smell definition from another paper. Code smells are potential defects, refactoring opportunities, and code standard violations. And it will affect the maintainability, reproducibility, efficiency, memory rights, performance, readability, and understandability. And to find a common code smell for machine learning application, we mine papers, gray literature, existing bug dataset, and Stack Overflow post. We use a set of machine learning related keywords with a set of code quality related keywords to search for papers. We select papers based on the title and abstraction and apply snowballing on the papers. At last, we filter out 6 papers that can be contributed to the CodeSmell catalog. And for the gray literature mining, we use 2 groups of keywords. The first group is the same with the paper mining, machine learning keywords with the software quality keywords. The second group is combining the library keywords with software quality keywords. With these 2 groups of keywords, we get 2,170 gray literature entries in total. We follow this step by reading the title first, reading the summary, and then reading the whole article and filter out 8 cornerstone blog posts. We use the replication package in the paper and period study on TensorFlow program bugs to identify some potential coding defects. Since the replication package only contains coding issues from TensorFlow, we did complementary Stack Overflow mining for other machine learning libraries, such as PyTorch, scikit-learn, Pandas, NumPy, and SciPy. And at last, we collect some code smell and coding practice and here is the catalog. We link this smell to different type, different pipeline stage, and the effect. We also build a website representing this smell. I will briefly introduce some smells in the catalog in the following slides. So this is the unnecessary iteration smell. In this two coding example, the loops in the red line can be replaced by the vectorization or reduction solution in the blue lines. In practice, loops are inefficient and wordy. Developers should avoid this iteration whenever possible to improve the software efficiency and reduce the code complexity. And this is the hyperparameter not explicitly set smell. The default hyperparameter of the learning algorithm API may not be optimal for a given data or problem, and even it is, the default hyperparameter may change in the new version of the library. Therefore, we recommend to set a hyperparameter explicitly. What's more, it will be easier for developers to replicate the model in a different programming language if the hyperparameter is explicitly set. And this is the memory not free smell. In this code example, the coding issue is if there is a model crashing in the loop, the size of the global state will increase along the loop. So the memory usage will increase over time. But if you use clear session API, the memory can be released instead of accumulating. Therefore, we should check whether the clear session API is used in the loop. Other libraries may also have the same kinds of memory release API. And chain indexing is a bad practice in pandas. When we use df blanket core blankets x here in the red lights, this is called chain indexing. Pandas sees this operation as two events: core df blanket core first and core blanket x based on the result the previous operation gets. On the contrary, df dot log blanket x comma core only perform a single call. So in this way, the second approach can be significantly faster than the first one. And furthermore, assigning to the product of the chain indexing has inherently unpredictable result. Since pandas may not guarantee on whether df blanket core will return a view or a copy, the assignment may fail. So this kind of code smell is specific to pandas API. If jury occurs on the data cleaning stage, it will result in less efficient and more error-prone code. So we have some discussion and implication retrieved from the result. First of all, we will say that it's still early days of the machine learning specific code smell research because after mining all these resources, papers, great literature entries, GitHub commits, and Stack Overflow posts, we only get 22 machine learning specific smells. There are a lot of material talking about the generic code smell like duplicated code, but not a lot talking about the machine learning context specific smell. And the ecosystem of AI framework is changing very fast. Now there is TensorFlow 2.0 and some issue with the TensorFlow 1.0 doesn't exist anymore. So we believe that some smells may become obsolete in the future. And in addition, some of the smells we identify are reported in the official documentation of the library. Yet there is still code being created that does not comply the recommendation. For example, the chain indexing smell. So we believe that the library maintainer should keep promoting the best practice while some static analysis tool can be created to help the application developer to identify this code smell and avoid them. And what's more, we also noticed that some smells are related to the context. For example, the deterministic option in the PyTorch should be set to prevent the irreproducibility in the development, but it doesn't need to be set in the production for better efficiency. Therefore, I think it will be cool if there are some context-aware study. Generally speaking, we believe that improve the machine learning code quality requires a continuous effort between the practitioners and academics. And in conclusion, we provide a code-smell catalog for machine learning application in our work. Future work includes developing a static analyze tool to automatically detect these code smells. And actually, we are already working on this. This is DS Linter, the static analyze tool for detecting the code smell mentioned in this paper. And now we are in the experiment phase. Feedback are more than welcome. If you are interested, please check out our GitHub repository. And since we also would like to learn more about the smell, we make a survey about the perceived severity of the cold smell. So if you are interested, please fill in the survey and share your opinion. And thank you, Luis. Luis has sending out the links in the chat. And this is my presentation for today. Thank you for listening. I will take questions.
Hi, I can ask a question if.
Yeah. Sure.
So thank you for the presentation, and we meet again, but virtually again. So I saw a lot of examples from Python, right? So would you say that your smells were the smells that you found, were they sort of specific to Python, or were they agnostic to the language you're using?
So we would say that yeah, we did the research in mining the lights that overflow related to the Python library, but like the hyperparameter not explicitly set smell, I think it also applies to like Java written machine learning project. We also recommend you to like set the hyperparameter explicitly in the Java written machine learning project. But yeah, I think the further study should like involve in the future world to see if there is some difference between different language and the machine learning application between different language. Yeah.
Okay, thank you.
Thank you for your question.
I think we also have a question from Sridhar. Maybe Sridhar, you want to make the question yourself?
Oh, I don't know. Can you hear me?
Yes, I can hear you.
Okay, I think this is pretty interesting work. I was just curious in terms of if you look at ML applications, the code itself is pretty less, right? So did you observe that in terms of like how much of the percentage of code is present? If so, how significant would it be in terms of code smells? Any thoughts on that?
You mean like the machine learning code is just a small part of the whole system, right?
Right.
Yeah, that's true. I also noticed that like in our study, it's the small part of the whole system, but I would say that it's the core part. So I think we still need to pay high attention to the code quality here because it's the core system like some code might affect the efficiency. So it's just a small percentage of code, but if you like set the option differently, it may significantly influence your efficiency.
Okay, yeah, thanks. So I was actually thinking in terms of assume that if I use a library like TensorFlow or PyTorch, the code within that would that have an impact rather than the code that I write for invoking that ML library. Uh, okay. Anyways, I was just curious to see if you have had some insights on that.
Yeah, so you mean like the different library? Uh, I'm not sure the latter part of your question. Can you?
No, I was asking like if you have to write code for an ML application, you may invoke code, you may invoke a library, right? Let's say, I want
Yeah,
to, do a random classifier or a random forest, right? So I would invoke code. Now that code is only one line, but what is happening inside that code may be long.
yeah,
So
that's true.
is that did you get into that or you looked at this one line of code or like the
Yeah,
piece of
so
statistics?
Yeah, we didn't look inside to the library itself. We just look into like one line of code and look into the application
Okay.
side of the code. So I think it will be definitely interesting to look into the ML library to see how we can like improve in the machine learning library side to improve the efficiency, reproducibility, things like that. Yeah, it would be
Okay,
interesting.
yeah, thanks. Thanks. Yeah, thank you.
Thank you for your question.
Okay, thank you. If are there any more questions? If not, let's thank Haijing again. And if Harold, I think is next. Harald is next, and he's gonna now move us to data smells.
Exactly. So can everybody see my slides?
Your slides.
Okay. Does this sound good?
Sound
Yeah,
is good.
perfect.
Everything's perfect.
Okay. So hello everybody. My name is Harald Voidl. I'm a PhD student from the University of Innsbruck in Austria. And I present the paper which I worked together with Michael Felderer and Rudolf Ramler about data smells, categories, causes, and consequences, and the detection of suspicious data in AI-based system. So I want to start with motivating the topic. So potential data issues are becoming an ever-increasing problem. So what are these potential data issues? These are, for example, ambiguous and extraneous values, synonyms or homonyms, etc. So these issues cause technical debt and data-induced bugs in AI-based systems. For example, a recent study identified data debt as an own technical debt type in AI-based systems. Moreover, a study about COVID software projects found that the second most common bug type in such projects were related to data. In addition, an AI-based clinical decision support system developed by IBM suffered heavily from potential data quality issues, for example, acronyms, shorthand phrases, or different styles of writing. So now the problem is that typical data validation components in the AI-based system lack to identify such potential data issues. Moreover, previous research did not treat these potential data issues in detail. So the goal of our research was to conceptualize these potential data issues in the form of data smells, by analogy to the code smells concept from the domain of software engineering. So we tried to provide a precise definition of data smells, find or define their characteristics, also identified categories, and find some catalog of these data smells, and also elaborate on their detection and use. Further, we try to outline the importance in AI-based systems regarding their causes and also their consequences. So now let's have a look what are data smells. We define data smells as context-independent, data value-based indications of latent data quality issues, which are caused by poor practices that may lead to problems in the future. So data smells are indicated by moderately suspicious data values, patterns, and representation. So now let's have a look at an example. Here we see a term which states New York. At the first glance, it seems quite fine. But we actually do not know if the state or the city is meant by that. So as the degree of suspicion can increase or can decrease, we see here an example about the term New York City.
Now here, this term has a very low suspicion. So it's rather clear what is meant by it. In contrast, on the other side, we have a term with a very high suspicion. There is a spelling mistake in, so it's rather clear that here is something wrong. And coming back to this moderately suspicious data values, like here, for example, New York, these are exactly what we see as data smells. So now I want to continue my talk about placing these data smells into the context of previous research. So previous research basically divided data quality issues into context-dependent issues and context-independent issues. So we went one step further and further subdivided these context-independent issues into obvious issues and latent issues. So examples of obvious issues would be missing values, duplicated values, or outliers. They are easy to spot and typically detectable through basic data profiling techniques, for example, descriptive statistics. In contrast, these latent issues are not so easy to spot. For example, synonyms, homonyms, intermingled data types, and what we see as data smells. So in our research, we conducted a literature review, including scientific literature and gray literature, to identify data smells and also to find some categories of them. We came up with three main categories of data smells. The first one is the category believability smells. Those describe semantically implausible, but usually understandable data values. For example, the suspect precision smell or the dummy value smell. The second category is the understandability smell. These smell typically refer to semantically true, but problematic data values. They are problematic in that sense that they are hard to interpret. We made two further subcategories of this understandability smell. One are the encoding smells, for example, a time encoded as a string, and syntactic smells, for example, a casing smell. The third category we identified were the consistency smells. They describe the use of inconsistent syntax with respect to the data values that may lead to interpretation issues. Examples would be a spacing inconsistency or a precision inconsistency. Now let's have a look at the causes of data smells. So data smells basically can occur through poor intrinsic quality of data sources. For example, consider a column name in a relational database, which is used in different tables, but with different data types. So a developer who wants to gather data from this database easily gets confused and introduces an error. A further cause of data smells would be the violation of recommended best practices in data management, software, or data engineering. For example, careless data entry, inconsistent data collection or transformation processes, or not using a data dictionary. The third cause, which we identified, is poor data generation, acquisition, or processing. To illustrate this, look at this code example here. Here we have a date string, which should be converted to a date object in Python. So a developer applies this method, and Python outputs this string here, but adds this time suffix to it. And this is a problem because developers are usually not aware of this because they only input a date into this function. So this time suffix, which is added, can make problems in the further processing of the data. We define these smell as a date-time smell. To avoid this smell, developers usually have to call another method, so that only the date is really the output of this function. So the problem now here is also that in data processing, there is often the technique of method chaining applied. So methods are typically chained each after one. And so such intermediate processing results are not easily to spot. So these are hard to identify. Now I want to continue by talking about consequences of data smells. So basically, data smells increase the likelihood of future problems in the evolution of data-driven systems and in data processing and knowledge generation. So coming back here to the problems occurring in the evolution of such systems, consider an ambiguous date or time format smell. For example, shorthand date or a 12-hour clock format. So if developers have to deal with such date formats, they cannot be sure what is really meant by it. There is a missing here AM or PM designators, so they can easily cause problems. Moreover, the handling of data smells often requires some data processing codes, which easily leads to pipeline jungles or glue code in such systems. Now, going on here with providing two examples about data processing and knowledge generation problems. Consider this intermingled data type smell. So when we look here at this column, at the first glance, it rather sees okay. It looks like integer values, but we have one intermingled data type here. And now the problem is that most data processing libraries apply an automatic data type inference algorithm, which chooses the most flexible data type for a column. So in this case, only one row is sufficient that the whole column gets a wrong assigned data type. As a next example, maybe consider here the casing smell, where we have an application about countries, about the United States, and in case the US came in a lowercase format, the machine learning model might define it as a new instance. Seeing this from a more holistic perspective, considering that machine learning systems often have direct feedback loops or continuous learning strategies, they apply serving data as the new training data, or are composed one after each other. Such small data issues can really propagate and cascade through such systems to huge problem over time, leading to a gradual regression of the performance of these models. So now let's have a brief look at detecting data smells. We developed two tools. One is simply based on rules to detect data smells, and one tool uses a more advanced learning approach based on machine learning techniques. We applied these tools on more than 240 Kaggle datasets, comprising more than 42 billion of rows. So what did we find? We find that most datasets, that is 120, had 3 to 5 smells. 3 datasets had no smells, and 45 datasets had more than 10 smells. So we can conclude that data smells are present in real-world data, but our detection resulted in a manageable size of these data smells. Now I want to show 2 exemplary smells, which we found during our evaluation. Here on the left-hand side, we see data about medical appointments. And here we identified this time suffix, which is added, which would be the date as date time smell. On the right-hand side, we see data about the pandemic, and we identified this ambiguous date time format smell. Here is no year mentioned or stated, so we do not know to which year this belongs. Now, coming to the use of data smells. For what can we use data smells? We can use them for the identification of problematic data sources prior to production. We can to guide data validation efforts, for example, to focus on the smell density of data streams when validating data. We can also use them to software quality assurance, for example, to uncover subtle issues or for mutation testing. Concluding, data smells can be seen as data quality issues that are present and can cause issues, but are not obvious now. That is, they are hard to identify. They typically arise through poor practices and threaten AI-based systems. Possible future work to consider would be the identification of less or more influential smells and the identification of smells for specific domains, for example, medical domain or the finance domain. Yeah, that was my presentation. Thank you very much.
Thank you very much for the presentation. We have time for maybe one quick question. And Rita put one in the chat. Do you want to ask it in person or should I ask? So I'm going to ask on Rita's behalf.
Yeah.
Basically, he was asking about, like you showed the catalog of the different data smells, and Shida wanted to know what are the sources where the catalog was produced from? Like
Yeah.
how did you compile it?
Yeah, we used data defect taxonomies from the scientific literature. There are some taxonomies out there which describe data issues. And we also used some data quality software tools which detect data quality issues. This was basically our sources, so scientific and gray literature.
Cool. Thank you so much. We're going to have more discussion after the next presentation. And now I'm going to ask Arumoy to share his screen. And Arumoy is going to talk about data smells in public data sets.
Thank you. So can everyone hear and see me okay?
Yeah, it's perfect.
Yeah, perfect. So good evening from the Netherlands. I'm Arumoy, and I'm going to present our paper titled Data Smells in Public Datasets, which was also co-written by Luis and Ari, who I believe are present in the audience somewhere. So a quick overview of the presentation. I'm going to present the problem that we're trying to solve first, along with the contributions that we made there. We'll take a look at the methodology that we followed, some brief results, and then I'll also present a select few smells from the catalog, which I think are interesting, at least to me, and I hope that is going to spark some discussion there. Finally, we'll conclude the presentation with some high-level takeaways and then limitations and future work. So let's get started. So when we look at traditional software systems and machine learning systems, so in traditional software systems, we typically see growth or maturity through change in code, right? But then when we move over to software systems with machine learning involved, we typically see three pillars now, right? So there's always change, not only in code, of course, but then also in the model and always and also in the data, right? And so all these three pillars of change are intertwined with one another. So typically the saying is that change anything, change everything policy, right? So if we have a minor bug or even a simple change in the data, we need to retrain the model, redeploy it, and continue monitoring it. Right? So everything is intertwined with one another. So it becomes really important to catch these problems early on, which typically stands to be in the data domain of the work, right? So machine learning, as we know, and as we also saw from the previous discussion with the group, it's all about the data. It's very data-centric. And so if we put a software engineering lens on it, I think that data to data scientists is what code is to software engineers. And so we have a lot of tools out there for software engineers to work with the code, but we typically see that's quite lacking when it comes to data science, right? And so that's what we wanted to work with, or at least help improve it in a minor way. So our research questions here to begin with was to identify the recurrent data quality issues that we see in public data sets. And so our contribution here was to provide a formal definition of data smells, and we defined them as anti-patterns in data sets that may indicate early signs of problems or debt. And our second research question here was to gauge the prevalence of the data quality issues that we are seeing. And so here we contributed by creating a catalog of 14 data smells, which we analyzed by analyzing 25 popular public data sets manually. So a brief look at the methodology here. So we have 3 distinct phases, and I'll talk briefly about each of them. So we first begin with the data selection phase. So here we pick data sets from Kaggle, which is an online data repository, and then we sort them by most votes, and we also put some inclusion criteria primarily on the format and on the size, and then from there we shortlist our data sets. After that comes the smell detection phase. So here we analyze each of the data sets manually using a set list of things that you would generally do when you're trying to understand the data. So this includes looking at the head, looking at the tail, reading the documentation if it exists, looking at the descriptive statistics and stuff like that, and then identify the smells that we're interested in. And then finally, we create our catalog. And so here we take the smells that we observe and we hold them through some exclusion criteria. So primarily, we exclude smells that don't apply beyond a certain language, programming language, I mean, or a certain tool set, right? And then from there, we create our final catalog of 14 smells. So I wanted to present, let's say the meta-analysis, and I think this plot depicts this quite nicely. So this is actually a 2D histogram, but we like to call it the matrix plot. So here we see the data sets along the x-axis, and then the smells that we identified along the y-axis. And so, at a glance, we can see where the smells, which smells, first of all, occurred more frequently, and then in which data sets. We can also see 2 marginal plots. So on the marginal plot along the y-axis, we see a count plot of the smells that occurred across the data sets. So essentially, it means that the presence of redundant correlated features was the most occurring smell, and I'll also talk about this smell in a bit more detail shortly. And then along the x-axis marginal plot, we see the total count of the smells in each data set. Right? Moving along, as promised, a few interesting smells, and I'll start with the presence of correlated features. And I think this one most of us are probably already familiar with. But the reason I bring this up is because this was the most frequently occurring smell that we found. So in our analysis, 19 of the data sets contain this smell. It's pretty simple. So if we have two correlated features, they typically change in a similar manner, right? So if we induce a change, a positive change in one feature A, we are going to see the same change in feature B. So this presents opportunity to create a more efficient, a smaller data set. And as we know, any little optimization in data science or in machine learning helps, right? So it's a highly iterative, highly experimental process, and we might be dealing with a really large data set. So any optimization helps here. Moving on, we look at the presence of sensitive features, and I want to motivate this one with an example. So here we see a probability density graph from the adult census dataset. So for those of you who don't know this dataset, it primarily contains census information of individuals. And among the features, we have the sex of the individual, the race of the individual. And the supervised learning task here is to predict the income class that they belong to, right? So there's a lot going on in this plot, but I primarily want to focus on the top left here. So here we see that for this data set, if we were to pick an individual who was male and of a fairer skin, they're likely to earn more, right? And also, if we compare between the two sexes, so male and female, we also see a discrepancy here. So if we were to train a machine learning model here with this data set and test it with a subset derived from this distribution, it would do well, right? But then putting that model into production would be a disaster, right? Because we see a history of bias in the data. Obviously, we don't want to reflect that when we move to a productionized system, because that does not reflect the real world. And we already see issues like this when financial institutes try to predict loans for people, or when the criminal justice system wants to predict the severity of the sentencing for a criminal, and when police tries to predict who is a threat using video surveillance, right? Okay, so switching gears, we move on to the third smell, and I'm doing pretty good on time, I think. So, and this one's the hierarchy from label encoding. So again, we look at the same data set, the adult census data set, but we look at now the education feature and the class, right? So this is again a probability distribution plot, and here what we can sort of grasp is that for this data set, an individual with a higher level of education is more likely to earn. Is more likely to earn more. And so this sort of information is quite important for a machine learning model. And what we typically do in data science is to encode this categorical feature into a numerical representation, right? So here, an instance, as an example, we can encode it using going from the lowest level to more advanced level, and then we can increase the number in a way so that we expose the hierarchy that's present in the categorical feature. And so this would be typically considered a good approach, right? So, but then what happens when we use the same technique for gender, or what for the race? So I think that this would be pretty bad, because we would introduce a bias into the model here. So the model might infer a higher income because of a bigger number, and we don't want to do that. So I already spoke about that, and I think I will skip the other two that I prepared in the interest of time, and to discussion. So I'm going to present two high-level takeaways from from this study that we conducted. And the first one is that we found several instances where there was a clear lack of proper documentation, right? So if we take a look at the heart data set, we see these very cryptic names like CP or TREST BPS. And so we don't know what these columns refer. We probably have to do more research or try to find some domain expertise here. Right? If we look at the heart data set, we have the sex column, but we don't know which is which. And also, if we look at the cancer data set, we have these numerical features, but we don't know the unit in which they were measured. So the takeaway here is that I think every data set is unique, and they have their specific idiosyncrasies, right? So without proper documentation, we don't really know what we are getting into. So providing this useful metadata or this context is really important, not only for a young practitioner, but also for experienced data scientists if they come back to the data set again after some time. So it gives them that context back again, and they can familiarize themselves with the data much quicker. And we also saw a study that came out of ING, which is a financial institute here in the Netherlands. And they found that AI practitioners typically spend most of their time documenting existing data pipelines. So we see that there's a clear need to write better documentation, but we also see that tools to aid practitioners in doing that is severely lacking. And then finally, we see technical debt from lack of best practices in upstream processes. So if we take a look at the Netflix dataset, so this contains data regarding content on Netflix, and we see two types, right? So movies and TV shows, and the duration is mixed, right? So here, maybe it's easy to derive the numeric value here for movies, but then how do we interpret seasons, right? So this is a huge challenge here, and it's not that easy to do this, or it requires severe effort. Again, if we look at the hard columns, the columns for the hard data set, better column names would be the first place to begin to aid the practitioner to get started faster, right? And then here, a simple addition of the measured could be a huge productivity boost for practitioners. So we think data smells can help identify these problems early on, and I think that's really important because the complexity is much lower, and then fixes come cheaper and easier, right? And then it's also important when you're working with stakeholders and you have a financial constraint to work with. So it can help estimate the problems that you're having and your effort in a better way, right? And deliver your projects on time. Limitations and future work. So as you may have noticed, we used a shallow as opposed to a deep analysis. And what I mean by that is specific of analysis that we did on the data sets. So we did not take a data set and fit a model to it and make some predictions. So the reason for doing that was to have a set of steps that can be replicated and scaled across multiple data sets. And also, we think that as you go deeper with an analysis, the smell becomes very domain or data set specific, right? The smells are linked to the version of the data set. Unfortunately, we can't change that. That's the nature of working with data. We do make in our paper we provide the version of the data that we use to analyze, along with the link, of course, to download it. We don't know the impact of a smell. So for instance, I talked about the smell of unknown units. So we don't really know what impact that smell has when we train a model on it. So does the smell have an impact on the accuracy or whatever metric that you're looking at for your model? And this was deemed beyond the scope of the study, primarily because this is a really involved job, right? So we would have to find data sets that had these smells, train multiple models, and then becomes an intensive experimental work there. And then finally, smells are subjective, but this is a limitation of code smells as well. So in code smells, not every large method is bad, and we do see God classes in real world public projects. And so finally, future work, of course, I think growing the catalog and analyzing larger data sets would be a good start. But then we are also looking at smells in different data types. So we only focused on structured. That's the most common type of data that you find. But then also it would be interesting to see semi-structured and unstructured data sets, right? And then finally, it would be also nice to look at the co-occurrence and evolution of smells. So some smells we noticed occur together, and then it would sort of link them to the entire machine learning pipeline and see how they evolve. So with that said, thank you all for attending and listening to me. I want to make two final remarks. So first of all, we took a lot of effort to keep everything open and reproducible. So the paper is, of course, open sourced under the Creative Commons license. But then we also have a website where you can actually take a look at the analysis that we did with each data set. And I have the adult one open here. And then also, if you scroll further down, you can also see the entire catalog that we created, along with how to identify the smells and potential fixes. And finally, thank you for your patience, but one last remark. So the project or the paper that I presented was to help practitioners with data understanding. So when they are getting started with the data, but then once you know the data you're working with and you want to move to a productionized version of your model, you want to make the expectations that you have for your data set explicit, right? Rather than holding implicit expectations. So that's where data validation comes in. And for our next project, we're looking at is how can we make data validation better for practitioners. And so if you have any leads on how to find machine learning pipelines that are working in production with somewhat non-static data, or if you are generally interested in this topic, please do get in touch with me, and I would really appreciate it. So thank you all again, and please ask me questions.
Okay. Thank you for the presentation. I have questions for Arumai. So one question I have is, like you mentioned, like at what stage would you try to basically identify data smells and prevent data smells?
Yeah, so thank you for your question, but I think that the data smells should aid you to find more problems, deeper problems in your pipeline or in your data and whatnot, right? So, and for your first part, so we focused on the data understanding part. So it would be nice to also see, as I mentioned, which smells occur in perhaps a more later stage of your pipeline, or if they even occur in the first place. So that is something that we did not do. So the smells that I presented were focused primarily on the data understanding aspect of the machine learning lifecycle. Yeah.
Okay. I see Shita has a question, but first I would like to ask you to stop sharing, and then I would ask the other two presenters to join us on stage. And so I'm going to open up for general discussion and questions. But now first, Shita.
Hey, hi, thanks. I think, very interesting work. I was just wondering in terms of when you have this catalog of data smells, right? Is it, like, what is the impact of those smells? Did you kind of like get into that?
No. So the short answer is no.
Okay.
But we do recognize that as a limitation.
Okay.
Yeah.
Okay,
But
a quick short question, if Tom allows me, a follow-up question. Okay, not the impact per se, but the data that you have in the data sets versus like anything an industrial case study where the data is in production, right? I mean, did you encounter that? Because I see some work from your group on where you did work with data from industry. So maybe, this question is for Louis and I mean, if they've seen multiple projects. So data smells in public domain data sets versus data smells in an industrial context.
Since you referred my name, I decided to turn on the camera. Maybe I can take over this question. So indeed, we were not looking at data that is actually in production in the pipeline. And that is a bit of a challenge, I think, for most of the research we see nowadays on data-centric AI. So it's really difficult to get access to data. And when you have access to data, it's very difficult to publish about it. People get nervous about publishing any sort of details, especially when it comes to issues in terms of quality. So I'm afraid I don't have a good answer for that question, Sridhar. I mean, we would expect some of these smells to be appearing in industry contexts, especially the problem with documentation. I wouldn't say that we would see lack of documentation, but from our previous observations, we would see people complaining a lot about the fact that it's really hard to write all the documentation that is required to comply with the processes of the organization or regulations or whatnot. So that would be the main difference that I would see between the data sets that we are looking at and the data sets in the industry.
Thank you so much. I want to give Harald a chance to talk about the impact of data smells, if he has any comments about it.
Yeah. We discovered or we see the impact of data smells really according to the algorithm, to the machine learning model. So machine learning models are really heavily dependent on the data quality. So such subtle issues which have a latent character can easily causes really a degradation of the performance of machine learning models.
Okay. Like another thing I was wondering is like, I think it's really interesting, like these code smells and data smells. And so I was wondering like how you see the link of a connection between these two types of smells. And I want to give Hai-Jin a chance to respond first.
Yeah, I think it will be interesting. I think there is some connection between the code smell and data smell, because like some codes are some code smell are in the data processing stage. Yeah, but we haven't investigate into the connection between code smell and data smell, but I think there are definitely some connection there.
Yeah.
Harald?
Yeah, I definitely see that code smells can really cause data smells, and also the data smells maybe also can cause some code smells emerging, because you have to deal with these data smells and then you introduce a code smell.
Yeah, like
I see this topic really interrelated, and would be interesting to investigate which code smell really causes which data smell.
Yeah, and like how the data smells can be prevented by better code, maybe.
The other way around, right? So if you address some data smells or some issues with your data, does your code smells change? Or at least it would be interesting to see how those two, interact with one another, right?
Yeah.
Yep. Cool. So we have about 2 minutes left in the session. So the one thing which I think all of you mentioned also is like the prevention of data smells and the different, or code smells and the different stages where you can prevent smells. And if you have any thoughts or ideas on what is the right point of time, because like you can show people there's a smell once it happens, but can you do something maybe before?
Yeah, I think basically as early as possible would be to find these smells at best at the design stage or the requirement stage, that you hinder their emergence completely.
Yeah, for code smell, like we did developer static analyze tool to like detect this potential code defects in the code. We want to like when you're writing the code, we give you hints and help you like prevent this code smell before the code into production, or maintain the code quality, assure the code quality during development. Yeah, we think that this kind of tool may be helpful for that, for preventing code smell, and we still need like further investigation.
Yeah, I think basically as early as possible would be to find these smells at best at the design stage or the requirement stage, that you hinder their emergence completely.
Yeah, for the design stage, like we develop static analyze tool to like develop
May I add something there?
Sure. Yes.
So we have seen in the industry that there is this feasibility assessment. So before they